speaker of today is Marta Batoreo from Espírito Santo, and she will talk about the periodic points of symplectomorphisms.
Okay, can you hear me? Okay. So let me first thank the... Mais baixo? Louder, okay. So let me first thank the organizers for the invitation. It's a pleasure to give a talk at this workshop. So I plan to talk about periodic points of symplectomorphisms. So the idea is to give some results on the existence of infinitely many periodic points of symplectomorphisms, and I'll focus on surfaces. So my symplectic manifolds are closed surfaces. So I'll work with closed surfaces, and I'll basically distinguish three cases: the sphere S2, T2, and all other, I'll call them sigma G, with G greater or equal to 2. So, but before I do that, let me set some notation and give some preliminaries. Okay, so when I have a closed symplectic manifold, so working with closed manifolds, and I have a function h, so defined on M2R, time dependent, one periodic. I'll consider it one periodic in time. Then I can associate with this function a vector field, which we call xh by this equation. And this is what we call the Hamiltonian function, or the Hamiltonian and the Hamiltonian vector field. And to this vector field, we can associate a flow by this differential equation. Which we call the Hamiltonian flow, and the time one map is what's called, so the flow at time 1, which we sometimes just denote by phi h, is what we call the Hamiltonian. So Hamiltonian diffeomorphism. Okay, is it big enough over there? I guess this is small, but can you read it at least over there? Okay, good. Okay, I'll try. Sorry about that. Okay, so as we all know this, a Hamiltonian diffeomorphism preserves the symplectic structure. Bigger is a little better, and I said okay, and okay, sorry. But as we know, not all diffeomorphisms which preserve the symplectic structure are Hamiltonian diffeomorphisms. So there are not time one maps of a Hamiltonian flow. And for example, if we consider, so on the two torus, a translation, the horizontal translation by some angle theta, so my phi t at xy would be x plus t theta y. The time one map, so phi 1. This is, so theta not 1, different. Because at time 1, if theta is 1, at time 1 it's just the identity. So phi 1 is area preserving, so this is a symplectomorphism. So this is area preserving. And it has no fixed points. So phi 1 has no fixed points. And if you want, the Arnold conjecture tells me that every Hamiltonian diffeomorphism must have fixed points. So let me recall here. So if I have a Hamiltonian diffeomorphism, I'll write it this way. The number of fixed points of phi h, so of a Hamiltonian diffeomorphism, is bounded from below by a number which depends only on a topological invariant of M. So for instance, if phi h is non-degenerate, right? So in the non-degenerate case, so if phi h is non-degenerate, then we know that the number of fixed points of phi h is bounded from below by the sum of the Betti numbers of M. So the sum of the ranks of the homologies of M. So as long as we know the homology of M, we have this lower bound. So it must have fixed points. Okay, so this phi 1, it is a symplectomorphism, but it's not a Hamiltonian diffeomorphism. So in this talk, I'm more interested, this talk is basically about symplectomorphisms which are not Hamiltonian diffeomorphisms. And but before I move on, let me just say, okay, so I'll work with symplectomorphisms. These are the symplectomorphisms I'll work. Phi, which live in the identity component of the group of the symplectomorphisms. That is, they are connected. So they are connected to the identity by an isotopy. So I have an isotopy phi t. So phi of 0 is the identity. Sorry, upstairs. T. 1, phi 0 is the identity, phi 1 is this phi here. Okay, to such an isotopy, I can associate a vector field like this. d dt of phi t is equal to this vector field. Okay? And so let me point out that the set of fixed points of symplectomorphism is in one-to-one correspondence with one periodic orbits of the system associated with this vector field xt. And the periodic points, so what are the periodic points? Are just points fixed by some iteration of phi. So union of fix of phi k. And these are in one-to-one correspondence with periodic orbits of xt here with integer period. Okay. So if I'm in the Hamiltonian case, so the fixed points of the Hamiltonian diffeomorphism are in one-to-one correspondence with one periodic orbits of the Hamiltonian system defined by the Hamiltonian vector field xh. Okay. Okay, so so for such a symplectomorphism living here in the identity component of the group of the symplectomorphisms, so I have this isotopy, phi t. So I have phi t. To this phi t, I can associate the vector field xt by that equation. So I have my xt. To this vector field, I can associate a one form just by contracting omega with this vector field. Okay. This is a closed one form, and can average it over time and consider the cohomology class of this closed one form. Okay, so this lives in H1 of the first cohomology of M. But in fact, for this to be a well-defined homomorphism, this is called the flux homomorphism, and it's defined on the universal covering of the identity component of the group of symplectomorphisms. So this is a class of this isotopy that maps this class to this closed one form. This class, so I have this phi t connecting the identity to phi. This is my phi t. And this class is the class of my psi t's, if you wish, connecting here the identity to phi, which are homotopic to this phi t. Okay? So, so this is a map from here to here. It's a homomorphism. So let me say a little bit more about this homomorphism. So for instance, see, if this phi t is a Hamiltonian flow, this is just dH or minus dH, if you wish. So this is exact. So this is 0 here. Okay, so in fact, the kernel of this map, the kernel of this map flux, is the universal covering of the group of Hamiltonian diffeomorphisms. This. Okay. Now, if my M, for instance, in that example I gave in the beginning, on the horizontal translation on the torus by some angle theta. So go back to the example of T2. Example where I had translated this by some angle theta. So what is the flux of that? I don't know if I wrote that down now, right? What is the flux of this isotopy? So x plus t theta y. So if we identify this H1, so in this case T2R, with the homomorphisms of pi 1, in this case T2 to R, flux of this phi t is this map from pi 1 to R, and it tells me if I take an element in here in pi 1, it will tell me what is the area swept by this gamma living here in time 1. So for instance, if I look, let me just look at the generators. Pi 1, if I consider this my gamma 1, and this thing here, my gamma 2, okay, the image of gamma 1 is, okay, I start here at gamma 1. After time, so in time 1, it will be translated by theta. So the area of that cylinder is just theta times 1. Okay, so the image of this would be theta. If I look at flux of this phi t of now gamma 1, the other one, this one here, if I translate it by theta, the area swept in time 1 is just 0. Okay, so this would be 0. So if you want to identify H1 of T2 with R2, I would consider, for instance, I could write flux of phi t as theta 0 if I identify this with R2. Okay? Moreover, if we consider that flux, if my manifold, is a surface of genus G, then let me just point out that, so if my M is sigma G with genus greater than 1, then that map flux, so it's defined on the universal covering, but for these manifolds, it actually descends to the identity component of the group of symplectomorphisms. I'll fix here some area form. I won't write it. Okay. So it will go to H1 of sigma G R. And this can be identified with R to the 2G. So it actually makes sense to say the flux of phi is equal to some 2G tuple. And let me write it for now this way. So U1 V1, UG VG. These are just real numbers for now. So UI VI. You'll see why I call them U's and V's in a moment. What? Diga. Qualquer coisa. Ah, tá a bater. Deixa que eu tenho. Obrigada. Está melhor? Okay. Okay, so let me just. Okay, so again, I'll distinguish these three cases. S2, the sphere, the two sphere, the two torus, and surfaces of genus G greater or equal to 2. And let's see what we know in the Hamiltonian case, and I'll call it the symplectic case eventually, not Hamiltonian. Okay. So what we know about what? So as I told you, I want to give you some results on the existence of infinitely many periodic points of symplectomorphisms defined on these surfaces. Okay. So for S2. For S2, we know that, so for instance, if we consider the irrational rotation on S2, then I'll have S2. If I consider the irrational rotation here, I just have two fixed points, right? The North Pole and the South Pole. However, we know that actually, so Franks proved that if there are more than two fixed points, then there are infinitely many periodic points. Okay, so I'll write it over. I'm going to write it over here. So if the number of fixed points of phi h is greater than 2, then I'll have infinitely many periodic points. And this is due to Frank's. Okay? In the Hamiltonian case. So the here, this is S2 simply connected. So all symplectomorphisms are Hamiltonian. So there's nothing else here to say. So what about a torus? So for the two torus, what do we know? So for the Hamiltonian case, we have the Conley conjecture. So let me state it this way, that for a large class of symplectic manifolds, I have that the number of periodic points of a Hamiltonian diffeomorphism is actually infinite. So a large class, I don't want to go into details. I just want to point out that it was proved. T2 is on that class. Okay. So here I have infinitely many periodic points over Hamiltonian diffeomorphism. This was proved for the torus by Hingston. Okay. And it also holds for surfaces of genus greater or equal to 2. So again, here I have number of periodic points. Hamiltonian diffeomorphism is infinite. And I'll say here Ginsburg. Okay, so there are other contributions to other classes of, or to other manifolds, but here I'm interested in these two. Okay, so what about symplectomorphisms here and here? What can I say about, or when can I say that I have infinitely many periodic points? Okay, so for the two torus, there's this theorem by Ginsburg and Gorel, I'll write it here, that tells me that if the number of fixed points of the symplectomorphism is greater or equal to 1, then I have infinitely many periodic points. Here I need phi non-degenerate. I'll make a comment on this at the end of the talk, okay? So this is Ginsburg-Gorel. So now that we have all this, I want to tell you something about this part. So under which conditions can we say that we have infinitely many, or that a symplectomorphism defined here has infinitely many periodic points? Okay, so before I do that, I'll give you a construction, and you'll see why. Okay, I'll start with the construction of a symplectic flow. So let me write the construction of a symplectic flow. We call it psi t. So on sigma g, with g greater than 1, with exactly (2g minus 2 hyperbolic fixed points and no other periodic orbits. Okay, and then after I make this construction, I'll give you some results. I'll give you some conditions under which a symplectomorphism on sigma has infinitely many periodic points. Yes? Hold on, because... Yes. Okay. With the, yeah. Okay. So maybe I'll write it here or here. So there's this result by Leonardo, which is like a variant, if you wish, of the Arnold conjecture, when they say for the non-degenerate. So again, phi lives in here in the identity component of the group of symplectomorphisms. So in the non-degenerate case, they prove that the number of fixed points of such a symplectomorphism is bounded from below by the sum of the Betti numbers of the Novikov homology and this Novikov homology is associated with a closed one form, and the closed one form is, so here I have an isotopy, phi t. This phi t has this first cohomology class associated with it. So let me call alpha a closed one form which represents this class. So this is this Novikov homology is the one associated with alpha. Okay. Was that your question, or okay? So this lower bound may actually be 0, as in the case of the two torus with that horizontal translation. Okay, so it's not like, so sometimes it's a variant of the Arnold conjecture, but it's not like it gives the existence of fixed points. Okay, so how do I do this construction? So I'll start with the case G equal to 2. So I'll start with the case G equal to 2. And so I want to find a symplectic flow on sigma 2 with exactly 2 hyperbolic fixed points and no other periodic orbits. Okay, so how do we do this? So we'll basically consider 2 tori, and we'll glue them together somehow. So let me start with 2 tori and represent each one like this. So this is my first torus, T2. And here I have another torus, T2. And now I consider on this first torus an irrational linear flow here. So this would be x plus tu, y plus tv, where, so let me write u1, v1, because I'm the first torus. So v1 over u1 is irrational. So let me, okay, this is my flow line, okay, with the rational slope. And here, so this is my phi 1, I'll consider the same thing but with different, I'll have a U2, V2, and another irrational flow. They may be the same, or if you want to consider the same, it's okay. But since they can be different, I'll just call them U2, V2. So this is phi T2 at xy is x plus T U2, y plus T V2. So here V2 over U2 is irrational. And now let me draw it this way. Okay. So I have these two tori, and I'll glue them. How will I do that? So, okay, I'll consider an object. I'm sorry, I'll have to erase this. I'll write it here. So phi 1t xy x plus t u1 y plus t v1. So I'll consider an object obtained by a homotopy between a square and a circle. So it looks more or less like this. Apologies. This is a square, okay? It's sort of a homotopy between the square and the circle here, and here on the other side I'll have the same thing. It's symmetric, okay? And now what I'll do is, so what's the dynamics I'll consider here? I'll consider a Hamiltonian defined on this object this way. So close to the square, to these two squares here, I'll consider the height function. So the lines are just something like this. So close to the squares, the lines just do things like this. And here, close to this circle in the middle, I'll have, so let me write it up. The Hamiltonian close to the squares, so h of x, y, z. This is equal to z when I'm close to the squares. So my frame here, something like this. X, y, and z centered here, okay? So here it's given by z, and here I'll have two fixed points, one here on this side of the circle, one right here, one on the other side. I'll have an orbit that's basically the semicircle here, another one that does like this, okay? And when I'm close to that circle, I'll have a flow line going towards that fixed point. And if I'm above this line, it will go above, it will go up, reach the top, go on the other side, and do something like this. And the same thing here. Go below, go down, then go up on the other side, do something like this. So close to this circle in the middle, the function, the Hamiltonian is given by y times z. Okay, so I'll consider h to be something like, so when y equals 0, something like this, beta of y, and this should be 1 minus beta of y. Beta is just a smooth function that's, when y equals 0, y equals 0. Something more or less like this. So here, basically, I'll have one flow line that goes towards this fixed point. If I'm above this line, have something like this, and below, have something like this. And on the other side, I'll have the same situation. So again, here, I'll just draw this line going towards the fixed point. And so on this object here, I just have two fixed points, this one and the other one on the other side, and those are hyperbolic. I draw it like this and like this. Okay? Okay, and now, right? So what I'll do is look at this torus. I'll take a square here where two of the sides are segments of this flow line, a small square, okay? This is all small. And what I'll do is I'll glue this square to this one. So like identifying this side, I'll identify this side, for instance, with this one, and so on. Okay, I'll glue this here. And I'll do the same thing on some other square here. Okay? Okay, so now I'll call the resulting thing psi t of u1, v1, u2, v2, because they depend on these u1, v1, u2, v2. And I have these two fixed points in the resulting sigma, and I have no other periodic orbits. So C. Here I have no periodic orbits. Here, when I go in this square through this, using this line here, suppose I reach this line here. Then I'll go towards the fixed point, right? So it's not like it creates a periodic orbit. If this line is one that looks like this one here, or even one above, right? It will go there, go around, and when it leaves, since close to the square, this is the height function, if it came in this way, it will go out this way. It won't go out like this, okay? So I won't have periodic orbits, other than these two. Okay? Sorry? This is the minimal number of fixed points, you're saying, that I can get in a simplex, yes. I guess the Lefschetz theorem tells you that the lower bound would be 2g minus 2. Okay, so for g greater than 2, you basically do the same thing. You consider g tori. I'll do it. Okay, just a sketch here. Right, I will consider here a rational linear flow on each one of them. I'll glue the tori by an object that looks like this one, right? So here I'll have one square. And two of the sides are segments of the flow line. Here I'll have one square to glue to this object and another one to glue to this other object, right? So I have g tori, I have g minus 1 objects like this. So these are g minus 1. And so for each one of them, I have two hyperbolic fixed points. So at the end, I'll have 2 times g minus 1 hyperbolic fixed points. and no other periodic orbits. Okay, so let me also point out here that, so what is let me focus here on g equal to 2. The idea will be the same for g greater than 2. So flux of this psi t flux of this psi t of u1, v1, u2, v2 so this lives in the first cohomology of sigma 2, right? This is the one where I'm doing the of sigma 2. And the first cohomology is the direct sum of the first cohomology of these tori. And the flux here is given by u1, v1, and here is given by u2, v2. So I can just write this as being u1, v1, u2, v2. And so in general, the flux of psi t of u1, v1, ug, vg is u1, v1, ug, vg. If I identify the flux with the 2G tuple. Okay, so knowing this, okay, 15 minutes. Okay. Actually, it is possible to compute the Flohr-Novikov homology of this psi t. And I won't go into details about the Flohr-Novikov homology, okay? I'll just say the following. That, so for the Flohr homology for symplectomorphisms, so Flohr-Novikov homology. So if my, let me put it this way. So if I want to u1, v1, ug, vg. So it depends on more things. I'll just write it this way, okay? Sorry. So this flow has exactly 2g minus 2 hyperbolic fixed points. Those hyperbolic fixed points contribute to the Flohr-Novikov homology in degree 0. Okay, so I'll just say that this has rank 2g minus 2, and I'll write it this way. So f 2g minus 2 tensor with the Novikov ring associated with the flux of psi. This is in degree 0. So alpha is a representative of the flux of that psi t. I'll write it UV, okay, means this. And this is the Novikov ring, so the completion of the group ring of, so this is pi 1 of sigma over kernel of the map associated with alpha with weight homomorphism alpha over the ground field F, and here my ground field F is Z2. And I have no other periodic orbits, so in degree different than 0, sorry. The Flohr-Novikov homology is 0. Okay, this Flohr-Novikov homology, if I have an isotopy which has the same flux, then the Flohr-Novikov homologies are the same. So well, if you wish, I'm following Leonardo in most of my statements here. Or just Ono, I don't know. Yes. Okay, so let me call it maybe proposition. So if phi is in the identity component of the group of symplectomorphisms, non-degenerate, if phi is non-degenerate, and flux of phi, I know I can write it as a 2G tuple, so I'll just write it at U1, V1, UG, VG. And if this satisfies VI over UI irrational, then I know that the Flohr-Novikov homology of this, well, need phi t is equal to the one of the symplectic flow we constructed. Okay, so now with this information, so I know it has trivial 4 degree non-zero and rank 2G minus 2 here in degree 0. So with this information, it is possible to prove the following result that gives me the existence of infinitely many periodic points. So let me call it theorem. So if phi is connected to the identity by some isotopy, strongly non-degenerate, and strongly non-degenerate means, so not just one periodic orbits are non-degenerate, all periodic orbits are non-degenerate, okay? And flux, so not just, actually need more, flux of phi t or phi, again, satisfies VI over UI is irrational, and there exists a fixed point x naught with non-zero mean index, then the number of periodic points is infinite. Okay? So to prove this, I use Flohr-Novikov homology and the fact that I actually know what it is here. So the fact that I have a fixed point with non-zero mean index you know, if this does not happen, then I'll see it contributes to something in here which cannot happen. It's the idea. But see, if I have, for instance, an elliptic fixed point, it will satisfy this. Okay, so if I have an elliptic fixed point, then the number of periodic points is infinite. So let me write that as a corollary. So let me, so this condition, these two conditions call them star, which is strongly non-degenerate, and the flux satisfies this irrationality condition. So if star, phi is strongly non-degenerate and irrationality condition on the flux, plus there exists an elliptic x naught, then the number of periodic points of phi is infinite. So elliptic implies immediately this condition. So also, another result that looks pretty similar to Frank's result, you'll see why, is the following. So call it corollary 2. So again, if I have star strongly non-degenerate in irrational condition on the flux, plus the number of fixed points of phi is strictly greater than 2g minus 2, then I also have that the number of periodic points of phi is infinite. Okay, so these are basically the results I wanted to tell you about to fill in here this box. Let me just make a remark, which is the following. We need some non-degeneracy assumption. There's this example due to Frank's. I'll do it for the torus, but it also works for surfaces with greater genus. So this example due to Frank's, well, it's stated in a paper by Gainsbourg and Gurel, well, where it says it's due to Frank's. So consider the following situation. We are in T2 with a standard symplectic form. I'll write it dx wedge dy if you want the let's say circular, the standard symplectic form here. Consider this one form, I'll call it alpha naught, as minus v dx plus u dy. Then the symplectomorphism, if you want, associated with this one form. So let me say that there's this phi t associated with this alpha naught, which is, so this xy, it's the same thing, x plus tu y plus tv. So if if you want v or u are irrational, or v over u are irrational, v over u is irrational, sorry, then I have no periodic orbits on the torus. Okay, so let's just say I'm here on the torus, and I have here my flow line. I'll just draw locally what's going on, okay? I have here my flow lines. So what we can do is consider here small u. Let me draw it this way. A ball or a box, if you want. And what we'll do is we'll change slightly things in that small u. So what we'll do is we'll consider a Hamiltonian H that has a critical point in U. There are no Hamiltonian flow lines other than that critical point that are completely contained here in U. And so let me write it down. Consider H defined in U such that H has a critical point X in U, no Hamiltonian flow lines other than X are, how do you say, totally, I don't know. Contained in U. I'll show you the picture in a moment. And DH equals that one form alpha not close to or near the boundary of U. So here's what's going on. You have that picture, and we change it. To something like this. So now in that, so I'll consider now a one form alpha, which is basically alpha naught outside that U, and inside U is given by DH. And so here in U, now instead of having those lines like that, I'll have here something with this is my critical point of H, and close to it I'll have something like this. And outside it is the same thing as I already had here. And so this is degenerate, and I do not create any other fixed points or periodic points. Okay, so actually to have something on the existence of infinitely many periodic points, I need some non-degeneracy condition. Okay, so I have 2 more minutes, right? Yeah? Okay, so I'll say one more thing, which is the following. So it was proved by Ginsburg and Gurel that for CPN, not just for CPN, but that's what I'm interested right now, that for CPN, if there is a, so for in the, here all symplectomorphisms are Hamiltonian. If I have a hyperbolic fixed point, so if there exists an X not hyperbolic, then Hamiltonian, we have infinitely many periodic points. It was also proved, so this is Ginsburg-Gurel. It was also proved that for CPN times surfaces of genus G greater or equal to 2, that a similar result like this one, actually, so for symplectomorphisms, a similar result to this one, but actually I need some conditions on the flux of the symplectomorphism. But it is a result of this type. Hyperbolic implies infinitely many. So it is true for CPN, and it's true for CPN times surfaces of genus greater or equal to 2. But then this type of result is not true here, does not hold here. Because as we saw, that actually there is a symplectomorphism with finitely many hyperbolic fixed points and no other periodic points. Okay. So that was my last remark. Thank you for listening.